My name is Jake Grillo. I'm one of the mechanical engineers on the F51 Sustainable Energy Storage Project, sponsored by Mr. Butani and Professor Nori. We're very thankful for them for making this all possible, and for our senior project coach, Professor Schuster, for helping us along the way. We've set out to design an energy storage device that will be able to combat the bad parts of chemical batteries that we've seen in the past that has to do with recycling and manufacturing and mining. Some things that we just want to be able to stay away from in the future. And our new energy storage device we decided to pursue is a flywheel. So basically what we're trying to do is compete with something like a Tesla Powerwall, where this can be in conjunction with your house and your solar panels. And when you're overproducing during the day with too much solar, you can charge up the flywheel by spinning it faster and faster until you have a solid speed that can actually store some energy. Then when you want to get that energy back out, you connect it to a load and you're able to power whatever you want to power.
Hi, my name is Elise Coons. I'm a fourth year mechanical engineering student here at Cal Poly, and I'm continuing on for my blended master's program next year. And I'm going to talk about our chassis subassembly. So our chassis subassembly actually serves two purposes. It's both a structural support and also a safety feature. Since we do have a lot of rotating elements, we want to make sure that that is structurally sound and is fully supported. And then we added steel sidings on the faces and the top to ensure that even if those vertical elements at all broke or something else fractured in the middle, that whoever was around it would be safe as well.
Hi, my name is Jack Lynchy. I'm a fourth year graduating mechanical engineering student, and I'm going to talk a little bit about the bearing subsystem. For our bearing subassembly, this is a critical aspect of our actual flywheel to make sure that it spins freely with as minimal friction as we can. Ideally, we would have something like a magnetic or an air bearing to reduce a lot of that friction, but in this prototype we're using roller bearings with actual ball bearings within them. And that constrains our X and Y directions, but then in our Z, our vertical direction, that's constrained with a thrust bearing, needle bearing that sits on the bottom.
We were able to design our flywheel and our shaft to operate at 5,000 RPM, but due to budget constraints and not being able to balance after our manufacturing process, which is usually what happens with rotary machinery, we ended up knocking down our total RPM to about 250. So running our system at 250 RPM will be enough to prove our concept.
Hello, my name is Nick Schnorr. I am a fourth year computer engineer and computer science blended program major. Today I will be talking about the motor in our system. This will be the main way of putting power in and out of our system. This is a BLDC motor which takes in three-phase power. It has a 5-to-1 gear ratio which will provide the amount of torque that is necessary for our flywheel, and it will spin at speeds over 250 RPM.
Our braking subsystem consists of mostly off-the-shelf automotive parts, as we didn't want to reinvent or re-engineer any of the parts going into the system. This subsystem consists of both a rotor as well as a caliper that goes back to a handbrake. As the rotor is mounted directly into the flywheel, this reduces any load flow going through the actual system in the event of any heavy braking, so we don't have to snap any keyways or actually damage the braking system in the process.
It was important for our flywheel to have a large mass moment of inertia, because that's what was going to be able to capture all of our energy and store it in the system as it's rotating. So we made sure to spread out the mass on our aluminum disc as far out as we could, to 14 inches in diameter.
For our control system, there are three main components: the control box, the Arduino microprocessor, and the motor driver. The control box takes in the user input, which allows them to start the motor, stop the motor, discharge, and recharge, and also emergency brake. This goes into the Arduino, which processes these inputs and then provides the corresponding outputs to the motor driver. The motor driver then powers the motor at the correct speed and torque.
All of our testing was done in the Structures and Composites Lab in Engineering 4 on the strong floor. We wanted to make sure that it was fully secured for the safety of the users. For our testing, we wanted to focus on two main things: making sure that the power in could be held for a predetermined amount of time, and then also could be discharged onto a load. In our case, it was an LED. We weren't expecting a crazy amount of output power, but all of our tests were able to verify that a flywheel can maintain, store, and discharge energy. And a special thanks to everyone who helped us along the way, especially in the manufacturing part of our design process. Professor Giorgio helped us broach the middle of our flywheel to make sure that it could be securely attached to the shaft. Elliot, a shop technician from Mustang 60, fully welded our chassis and our frame to make sure it was structurally sound, so thank you to him. And additionally, Colin, a lab assistant for the Structures and Composites Lab, supervised our testing throughout the past couple weeks.
Thanks for listening.
Have a great summer. Okay, that'll be perfect.